Hi.
Hey, you want to scare your friend in high tip?
I had to watch that.
Imagine you're in empty space and you fire off a stream of electrons. Well then, according to most physics textbooks, the only way to change how those electrons behave is by applying an electric or magnetic or gravitational force to them. But most physics textbooks are wrong.
I'm gonna start you off by saying you don't know anything about science to begin with when it comes to the electron's path through space. I've already watched this video. Guess what I'm gonna rate this video? No, not an F, but just guess.
1950s, two physicists came up with a clever experiment. You could have electrons travel through a region with no electric or magnetic fields whatsoever, and yet, by flipping a switch, you could change their behavior.
The magnetic field could be just zero, and yet the presence of some quantity could actually lead to observable effects. That wasn't supposed to happen, right?
So the first thing that is happening is one. I'm sorry. How did you go about testing for whether or not there is an effective field influence outside of certain things? Let's see what they say.
The experiment split the physics community in two. It made them question whether fields are fundamental or whether something that was supposed to be just an abstract mathematical tool was actually more core to reality.
I'm gonna vomit. We already know that the way that we have these vector diagrams is to express the kind of attractive forces through gravity or magnetism from a distance towards whatever is doing the attracting. So it's not a question. Framing it as a question is like pretending to be an ignorant person. You can't do that. No one's doing that. It's like saying, oh, we found something new. No, you didn't.
This tool was first introduced in an attempt to solve one of the hardest unsolved problems in physics, the three-body problem.
Started with $1 and there's thousands of games. It's called Betty Casino, but you didn't hear it from me.
I sure fucking didn't.
Problems in physics, the three-body problem. That is, if you have three bodies and you know their initial positions and velocities, how will they move under the influence of each other's gravity?
It's a juicy problem which has occupied literally generations.
So I love how they go off topic entirely.
Hundreds and hundreds of years of incredibly ambitious, talented
move under the influence of each other's gravity.
It's a juicy problem.
Just so you have the name.
Literally generations, hundreds and hundreds of years of incredibly ambitious, talented mathematicians, physicists, and astronomers, and beyond.
The fact that this problem is so difficult to solve should at least be a little surprising. Because if you have just two bodies, then the solution is easy to find. In fact, the general case was already solved over 300 years ago by Newton himself.
But when Newton added a third body, well, that's when everything fell apart. In the two-body case, the forces behave predictably, always pointing toward the system's shared center of mass. But with three bodies, this is no longer the case. When you try to calculate the forces, they end up being extremely dynamic. In addition to worrying about the magnitude of the forces, you also have to worry about their direction. So you end up with this chaotic mess of vectors. For the next 100 years, everyone who tried to solve this problem failed. But what if there was some other way to approach it? A way to simplify the math and not have to worry about these three...
I'm sorry, did you have a free body problem where the bodies themselves are not going through space? They're not stationary, or they're not they're not going around each other, and also not. There's an inertia that happens when you all are moving forward in some direction through space, which almost everything is. So immediately as that happens, you have to have the field progress. Whatever.
Dimensional vectors. Well, that's where Joseph Louis Lagrange comes in. In the 1770s, he was also trying to solve the three-body problem, and he came up with a new approach. It works something like this. Say you've got a single mass, like a star. Lagrange imagined assigning a value to each point in space around the star. The value is determined by the star's mass and the distance from the star. You can think of each value as a height, and if we then turn this into an altitude map, you can see how the star creates this sort of well. What Lagrange had developed was the gravitational potential V, and what's important to note is that V is a scalar. It has a magnitude, but no direction. So the genius in Lagrange's idea is this. At any given point, we can draw an arrow pointing directly downhill, where the size of the arrow corresponds to the steepness of the hill at that point. We can repeat this process at every point, and if we then shift our perspective to 2 dimensions, look, what we've got is the gravitational field of the star. Mathematically, we say that the gravitational field G is equal to the negative gradient of V.
So Lagrange had found a way to switch the problem back and forth between one of vectors and one of scalars. And while adding up vectors is hard, adding scalars is a piece of cake. To find the combined potential landscape of any number of bodies, you just add up their individual potentials. And then you can always use that to get back to forces if you want.
This is something we haven't talked about for 30 years, but okay.
For a simple two-body system, like the Earth orbiting the Sun, that combined potential looks something like this. If you look closely, you see that there are 5 points where the gradient is 0. And so Lagrange realized the forces there are also 0, which means that at each of these points, you could place a tiny third body and it would maintain a perfectly stable orbit. That is, if it isn't disturbed. These points are now known as the Lagrange points. And while they didn't help solve the three-body problem, Lagrange was developing more sophisticated tools. In fact, he developed an entirely new way of doing mechanics. But for that to work, he didn't just need the potential. He needed the potential energy, and the kinetic energy too. I think when people hear potential, they think potential energy. And while they're very similar, there is a subtle difference.
So the thing is, I think they're trying to show like the earliest points of an idea that will become useful later.
You have the potential, that's basically the field corresponding to a single body. Then it will have some potential field around it, which is described as V equals minus Gm over R, where this is the mass of the sun. But to get the potential energy, we need to add in a second body. So let's say that's the Earth. The potential energy, let's call it U, is basically just the potential times the mass of the second body. So they're very similar, but they're slightly different. And the kinetic energy of the Earth is simple. That's, of course, 1/2 mv squared. So now we have everything we need to try this new method. In fact, we made a whole video on this over a year ago, but for now, all we need to know is that we can write down the kinetic minus potential energy to...
Yeah, they don't take all potential paths. That was debunked. So let's see them repeat their mistake.
Find what's known as the Lagrangian. Then you sub that into the so-called Euler-Lagrange equation, and out comes your solution. For example, predicting the motion of a double pendulum by using the standard forces approach is infamously hard.
Because as one pendulum is swinging, it provides the attachment point for the pendulum hanging below it. And so that pendulum is in this moving reference frame as it's swinging.
But if you plug the kinetic and potential energy into the Euler-Lagrange equation, then you can quickly get to a solution, at least numerically. That's actually how we made this simulation.
I remember thinking, man, force is like hard to get the right answer. You can do it if you're good, and people who are good at mechanics can do it. But with the Lagrangian approach, you could just write down the energy, which is a scalar, not a vector, plug it into the Euler-Lagrange equation, and you get the right equation to motion, and you don't have to be a good physicist.
But for all its usefulness, the potential wasn't enough to help Lagrange solve the three-body problem. In 1887, mathematician Heinrich Bruns finally proved that the three-body problem is unsolvable. There are simply too many unknowns and no way to simplify the problem to reduce them. So the best we've got are computer simulations which compute the potentials from moment to moment and use that to predict how the system will evolve in time.
And so that's what we come to realize.
In other words, in order to solve it, you have to do a number of calculations multiple times after every step, which you could do on paper, which makes it solvable. It would just take lots of paper and time, or whatever.
That the three-body problem is beautiful for what it's taught us, even though we now recognize that we can't actually solve for this exact problem as many folks had hoped to do. And in doing that, they merely gave us the machinery of modern mathematical physics. So I'm pretty happy they tried.
The potential helped simplify a wide array of problems. For many physicists, it even replaced forces as their primary tool. It became so useful that people started to wonder if other forces in nature might have a corresponding potential, starting with the electric force.
If you look at the formula for the electric force, you notice that it's remarkably similar to that for gravity, just with masses and charges swapped. In the 1810s, Simeon Denis Poisson, one of Lagrange's students, also noticed the similarity. And he realized that you can define an electric potential phi in a very similar way. But there is one important difference. And that is, while two masses can only attract, two charges can attract or repel. So now, with the potential, you don't only get bits, you also get hills.
But one force was much trickier to find the potential for, and that was the magnetic force. And that's because magnetism is a fundamentally different beast from the gravitational and electric force. Take a bar magnet. We can draw the magnetic field it produces. It looks something like this. Now, at first glance, this looks very similar to the electric scenario, where we have a positive and negative charge. But this picture doesn't look at what's going on inside the magnet. So if we reveal what's inside, then you see that these lines actually continue, but now they point from south to north. So magnetic field lines are actually loops. They don't have an origin or endpoint. And that fundamentally changes things. So physicists needed a new way to describe the magnetic potential.
Want to get the most out of CBC News? Use
No.
down.
Came in the 1840s from an undergraduate student named William Thomson.
His day job as an undergraduate was to learn as much fancy calculus as possible, and then when he learned all that, he invented more.
Thomson found that the mathematics of his day was unable to describe the relationship between a magnetic field and its associated potential. So he came up with an entirely new function, a curl. To see how this works, imagine the arrows of this vector field are like currents in a liquid. If we were to place a paddle wheel right here, it would start to rotate rapidly counterclockwise. As Thomson defined it, this spot has high positive curl. At this spot, it would rotate clockwise, but not as rapidly, so it has lower negative curl. And here, the current pushes on it equally in both directions, so it wouldn't rotate at all. This spot has zero curl. Thomson realized that the magnetic vector field B could be defined as the curl of some other vector field, the magnetic vector potential A. Now, even though they're both vector fields, it turns out that A is often much easier to work with than the magnetic field itself, much like the other potentials V and phi.
Thomson was showing there was a kind of underlying mathematical structure one could use that would streamline the calculations, but even Thomson thought this was a kind of device, a helpful device, and not a substitute for like the real physics.
Decades later, Thomson was elevated to the House of Lords for his contributions to science, where he received a new title, Lord Kelvin. With Kelvin's latest addition, there were now 3 fundamental equations relating the potentials to their respective fields.
Thanks to each of these, you could now solve problems much easier. And so, ever since, professional physicists often use potentials instead of forces or fields to solve the problems they're working on. Potentials even show up in some of our best physical theories of the universe. But that raises an important question. If potentials pop up everywhere, then do they actually represent anything physical? That is, can they have a direct influence on reality? Well, to most physicists, the answer was a resounding no.
Take the gravitational potential of a single star, for example. Well, we could just add 10 to each value of the potential, and this would shift the overall landscape. But the change in landscape from one point to the next remains the exact same. So the field is the same as the one we had before, and the force an object would experience at any point would remain unchanged. In fact, we can add any constant, 10, 100, a million, and the field doesn't change. And so the forces an object would experience going around it also don't change.
That doesn't make
There
sense.
are an infinite number of ways we could write the gravitational potential for any gravitational field and get the system to evolve in the same way.
And the same is true for electricity and magnetism. The value of the field, and thus the force, is fixed. But the value of the potential is arbitrary. So from this, most physicists concluded that potentials can possibly have any physical significance. It must just be a trick that makes the math easier. But most physicists might be wrong.
In 1942, 23-year-old David Bohm was hard at work on his thesis in particle physics when one day he received an unexpected visit.
Robert Oppenheimer, who was David Bohm's PhD advisor, wanted to bring him squarely onto the new Manhattan Project efforts.
This was a life-changing opportunity. Bohm would be working side by side with some of the top minds in physics. But there was a problem. The project's military director, General Leslie Groves, had to approve Oppenheimer's recruits. And when he ran a background check on Bohm, he didn't like what he saw.
He briefly joined the American branch of the Communist Party when he was in California. By his own recollections, he quit pretty quickly because he got bored. He said these people just sit around talking all day and don't do anything.
Even so, Groves deemed Bohm a security risk and banned him from working on the Manhattan Project. But things got even worse.
Just as he was about to finish his dissertation in Berkeley, the topic was then classified. He did not have clearance, so he couldn't even work on or even write up his own dissertation. So Oppenheimer had to certify that Bohm had done good work, and in 1943, in wartime, that was sufficient for Bohm to actually get a PhD.
After the war, Bohm became an assistant professor at Princeton University. But fears surrounding his communist sympathies followed him wherever he went.
Okay.
In 1949, he was brought before the House Un-American Activities Committee for questioning. While Bohm was under investigation, Princeton let his professorship lapse, and even after he was acquitted, the university refused to reinstate him. It seemed that Bohm was destined for obscurity.
Okay.
And so, Oppenheimer gave him a firm recommendation: leave the country and start fresh somewhere else. Oppenheimer was no stranger to political persecution, and he didn't want Bohm to suffer the same fate. So Bohm took the advice. His journeys brought him to Brazil and then Israel. And though he was free from the political pressures he had felt in America, he still found himself an outcast. Many of Bohm's academic peers were put off by his more unorthodox ideas, including his radical interpretation of quantum mechanics and his new theory of human consciousness. But there was one student who was enthralled by Bohm's approach, and that was Yakir Aharonov.
Never heard of this guy.
First of all, extremely bright, and also very nice personality.
Or this guy.
So it was beautiful to interact with him.
When Bohm relocated once more, this time moving to the University of Bristol in England, Aharonov chose to come with him. And it was there in Bristol in the 1950s that Aharonov and Bohm stumbled upon something huge.
For a long time, I was thinking more deeply about the interpretation of quantum mechanics. It wasn't to solve any problem. It was just curiosity.
According to quantum mechanics, at the smallest scales, particles behave like waves. And this behavior
Because you don't understand the EM field. Moving on.
is governed by the Schrödinger equation. The solution to this equation is called the wave function psi. If you take its modulus squared, you get the probability density of finding a particle at a given point at a given time. The left side of this equation tells you how the wave function changes over time and space. And the right side tells you that this change depends on h, what is known as the Hamiltonian. It's basically just the total energy of the system.
In the case where we have both an electric and magnetic potential, the solution to the Schrödinger equation looks something like this, where this is just a constant, and this term describes the complex phase. It looks complicated, but it's actually quite easy to get a feel for it. So let's plot it in 2 dimensions for an electron moving to the right.
The different colors here represent the different phases, and you can see how the phase evolves over time and space. Thank you to Richard Behiel for inspiring this approach. Now, if you look closely at the original phase term, you see A and phi, the magnetic and electric potentials. So watch what happens if we add a magnetic vector potential that points in the same direction as the electron is traveling. You can see that the wave stretches out, so now the phase changes more slowly over space than it did before. And if the potential points the other way, then now the wave gets more compressed, and its phase changes faster over space. And a similar thing would happen if you change the electric potential phi.
Now, this by itself, I think, wasn't shocking to most physicists. Just as you would always use the potentials to make the math easier, that's also why you use it in the Schrödinger equation. But really, what's responsible for these, even phase changes were still the fields. But you spoke to Aharonov.
Yeah.
And that wasn't his take.
No. If you look at the Schrödinger equation, you can't just replace the potential phi with the electric field E.
Why not?
Because you're losing information.
Okay.
Because remember, you can define any number of potentials for a specific electric field because you can pick an arbitrary height. But that information is lost when you go and swap it out for the electric field. There's another way to think about it.
Okay, this is getting real.
So if you have an expression like 5x squared plus 5, you'd think you could just write this as the integral of 10x dx, right? Because the integral is 5x squared plus
C. Right.
C is a constant, so it includes 5, but it also includes any other number. But importantly, C is not 5, or at least not in every case. So you lose this specificity when you go from a potential to an electric field, and Aharonov wasn't comfortable with that. So he thought, what if every quantum system was actually influenced by the potential and not by the field?
Right.
So it's the potential that shows up in the Schrödinger equation, so it is what influences wave functions. He had to find a way to prove that what we're observing is always because of a potential and not because of the field.
How do you do that?
Complicated. See, Aharonov had to design an experiment that would send a particle through a region where there's no electric or magnetic field, but there is a potential. In such a setup, if the phase of the particle's wave function started changing slower or faster, that had to be the direct result of the potential itself, because there are no fields.
Wait, you didn't tell me about this.
Well, I'm telling you.
But that's where you run into a problem, because there's no way to directly measure the phase of a particle's wave function. So how do you devise an experiment that can yield a measurable result? Well, Aharonov enlisted the help of his mentor Bohm, and together they came up with the following theoretical experiment. It starts with a beam of electrons, which is split into 2. In the middle of these 2 beams is a tightly coiled wire known as a solenoid. Now, solenoids have an interesting property. When you run a current through one, it produces a strong magnetic field inside the coil and a very weak field outside the coil. The longer the solenoid, the weaker the field in the surrounding space. For simplicity, Aharonov and Bohm imagined a setup with an ideal, infinitely long solenoid, one where the magnetic field outside the coil is exactly 0. After traveling on opposite sides of the solenoid, the electron beams are redirected back towards each other by the researchers. And here, at this point, they intersect. Now, since electrons behave as waves, the waves from the intersecting beams overlap and produce an interference pattern, bright fringes with gaps in between them. The exact pattern depends on the phase of each of these waves. When the solenoid is off, there is no magnetic field in the region the electrons are traveling through, and there is no magnetic potential. The phase of the electrons changes in the same way across both beams, regardless of whether they pass above or below the solenoid. And so you get an interference pattern that looks like this. But when the solenoid is turned on, well, there is still no magnetic field because it's confined entirely within the coil, but there is a magnetic potential. That may sound strange, but remember, the magnetic field is the curl of the magnetic potential. The curl of the potential can be 0 in some region, even when the potential itself is not.
When you have a coil of energy like that, the energy is flowing around the coil. It's a larger field. It moves circularly. Or the electric field, right? And so you can have it so that that is the energy that is outside. But of course, you would do control tests of the coil itself to have like little pins or something on the outside, see if they react, what they do. Like you can test for this without using electrons or how they are affected. You would know the influence of the thing, so you'd know if it was 0 or not.
And that's exactly what's happening here. Now, take a closer look at the vector potential. In the space the upper beam passes through, the potential points in the opposite direction as the beam. So here, the phase changes faster. But below the solenoid, it points in the same direction as the beam. So the phase changes slower. If the phase truly depends on the potential alone and not the field, then the phases of the two beams should evolve differently. So as a result, the interference pattern should shift when the solenoid is on versus when it's off.
The magnetic field could be just 0, and yet
the effect on one half and the effect on the other half are opposite points. And according to that, it gets compressed or stretched out depending on the angle of the field. Then you should have it stretch out on one side, compress on the other side, but then they interfere with each other once they recombine and are out of phase. That's what they're saying happened.
the presence of some vector potential could actually lead to observable effects. That wasn't supposed to happen, right?
What I love about this story is that it reminds me that individual people can challenge entire paradigms. For nearly 2 days to join the Planet Water on this QR, and now back to the mystery of the potential. Aharonov and Bohm published their findings in 1959, and the reception was mixed.
Certainly in the beginning, many people thought that it can't be true. So there were many people that tried to write articles against it.
Even Niels Bohr, one of the founding fathers of quantum mechanics, found it impossible to accept that a particle could be influenced by a potential in the absence of any force. But some physicists supported Aharonov and Bohm. Richard Feynman wrote, "The fact that the vector potential appears in the wave equation of quantum mechanics was obvious from the day it was written. It seems strange in retrospect that no one thought of discussing this experiment until 1959, when Bohm and Aharonov first suggested it and made the whole question crystal clear." Feynman included himself in that statement. He later wondered why he had never noticed the effect. Physicist Victor Weisskopf had a similar response. The first reaction to this work is that it's wrong. The second is that it's obvious.
Autodesk Flow Studio.
Ultimately, there was only one way to settle the debate. Someone had to actually do the experiment. The first to try was a colleague of Aharonov and Bohm's at the University of Bristol, Robert Chambers. Chambers' experiment largely followed the setup Aharonov and Bohm proposed, with one notable exception. An ideal solenoid would have to be infinitely long, which is physically impossible. So instead, Chambers used a tiny needle-like piece of iron, about 1/millionth of a meter thick, and 500 times as long. When this iron whisker was magnetized, it produced a magnetic field that was strong within the metal itself, but negligible outside of it, as well as a magnetic potential in the surrounding region of space. To get a baseline interference pattern, Chambers fired two.
You ever did that experiment where you charged like a nail or a hammer or something that was iron and it became a magnet? Bitches are forgetting physics right here. This is literally elementary. You charged it, it doesn't have magnetic field just inside of it. It is a magnet, the field is around it, emanating from it. How do you do this? How do you fail to notice that? It wouldn't negate the magnetic field. Listen, in order to negate the magnetic field, what you have to do is have all the magnetic field lines that are going out or in be all facing the inside and have it be sealed so that there is no magnetic going in the other direction. All you can end up with is a magnetic halt. This does occur. It can happen, but you didn't make that. You made a magnet. This is where you get a complete F for not noticing you made a goddamn magnet. This was fact-checked. This was fact-checked. Come on.
Beams of electrons around an empty region of space. Then he added the magnetic whisker. When he fired the beams again, the interference pattern shifted. It seemed that Aharonov and Bohm were right. But critics were unconvinced.
People objected to it because since the whisker is finite, there is always some magnetic field that will go out.
Maybe a stray field was responsible for the effect, not the potential.
And that's throwing no shade on their colleague who did these cool experiments. It's like, it's hard, right? It's really hard.
And so it went for several decades.
If you want to check the magnetic field, literally everyone has magnetic shavings nowadays. You can do that test so easily, and it just shows it to you. Where, like, you have that, or you got that magnetic liquid that shows you, or that you have, like, paper that's straight up, like, or it's a glass or something that shows the magnetic field lines inside of the thing. You can't. We have tools for this.
Experimentalists repeatedly tested the Aharonov-Bohm effect.
Just iron shavings, dude. It's so simple to do.
But each trial had flaws that left the result open to debate.
Until in 1986, a team of Japanese researchers led by Akira Tonomura came up with a new way to do the experiment. See, they used a tiny donut-shaped magnet to make their magnetic field. With a perfect torus, all the magnetic field is contained within the loop. Outside it, it's absolutely...
That is not how that works.
...zero. And as an...
That is completely not how that works.
...added layer of protection, the team also coated the entire magnet in a layer of superconducting niobium, which would block out any leaking fields. Now, previous experiments relied on turning a magnetic...
Okay, again. What's the point of the... No, you're not... Then you're not influencing the outside field whatsoever. It's then whatever field is around, and doing things naturally, and as the electrons are moving through it, will induce a thing. You gotta think about the electrons having their own influence in this, and their own push on the electromagnetic field on any objects, blah blah blah.
Field on or off. But Tanimura's team took on a different approach. In their case, the magnet is always on. But because of its unique shape, the potential outside the torus is different from the one in the center.
That's
it points
true.
towards us on the outside and away from us on the inside. And the team realized they could take advantage of this. They started by firing off an electron beam, which was actually wide enough to be treated as two separate beams. Part of it traveled along through empty space and functioned as the control, whereas the other part washed over the entire torus. And what's important here is that the beam is wide enough so that part of it passes around the torus and part of it passes through. Then, at the end, a biprism deflects the electron beams toward each other. They intersect, and this is where they create an interference pattern. Now, think about what this interference pattern should look like. Well, for starters, there should be a shadow of the torus, so we can fill that in. But the rest? Well, it depends on whether the Aharonov-Bohm effect is real or not. If it's not real, we'd expect to see an interference pattern that looks something like this, where the pattern outside the torus and in the center match up. But if it is real, then the electrons that traveled through the center would have experienced a different potential, which would have shifted their pattern by half a phase. So that should look something like...
Okay, let me explain to you 15 trillion ways about how this is the wrong way to think about it. Because you're recombining from electrons that didn't have that interaction. Right? Half of them, if you simply took the input of the single beam going through the experiment, and you didn't have the weird combining with the stuff, well, you wouldn't have an interference pattern. It depends on how you put the beam. The other half of the beam. Oh, whatever. The thing is, what happens with interference patterns is that they are the geometry of the EM field progression as it goes through the essentially what you did was a double slit where you have these two mirror points and that dot in the middle. Those slits are essentially wide. The interference pattern happens there. And again, the EM field is propagating along outside of the electromagnetic field. The question is why?
This. Now, here are the results from Tanimura's experiment. You
let me see it again.
These are the interference fringes inside and out.
Yeah, the phase. That's a much larger donut than expected. But anyhow. What happens with normal interference patterns with water and whatever else is about pressure and it's all wave pressing on both sides. With this, it's a different thing entirely.
Outside the magnet, and then if you follow what is a peak outside the torus, lines up with
a
trough inside the middle, and then it's a peak outside again.
And that's exactly what they predicted.
This is exactly what they predicted.
So it's real?
It's real.
Only the Tanimura experiment was really the final proof, experimentally.
And yet, soon a new debate emerged.
The effect is real, sure, but how should we interpret it? What is it really telling us about the nature of the universe?
Download BetMGM.
Telling us about the nature of the universe. Today, physicists largely fall into one of two camps. The first camp claims that potentials aren't just mathematical conveniences, they can influence physical reality. This is the perspective initially favored by Aharonov and Bohm. As they wrote in the abstract of their paper, contrary to the conclusions of classical mechanics, there exist effects of potentials on charged particles, even in the region where all fields vanish. Some take this position a step further. Since the potentials show up in the Schrödinger equation and the fields do not, well, they argue that the potentials are more fundamental to physics than fields.
You realize the electron beam itself has its own fields.
Richard Feynman supported this idea. He wrote, A is as real as B, realer, whatever that means.
I mean, I kind of like that interpretation, but something about the potential bothers me, and that's the fact that you can set the potential at any arbitrary height. It can be plus infinity, it can be minus infinity, anything in between. So wouldn't that change, how the potential actually influences the wave function?
This bothered me too, so much so that I actually ended up asking a professor about this. But it turns out it can't.
It's not just the potential that's entering the observable, it's the line integral. So it's only A that enters, it's not the magnetic field. B vanishes, it's only A, but it's not A alone.
It gets a little technical here, but, if I pull up,
as one does,
a flip chart, then we can actually run this through. So if you look at how the potential shows up, then what's measurable is not the phase directly, but it's the phase shift. Call it delta theta. Then the phase shift is the line integral of A over the path, or dotted with the path. So you get this. Now you can imagine, okay, let's add a constant to this. And if our setup is roughly, we start here, one electron beam goes like this, and the other one goes like this, and these are symmetric, then the potential here will point, let's say, in this direction. But here it will point in that direction. Let's say instead of A, we do A plus C, some constant.
Right.
Then when we're taking the path this way, we'll be adding that C, and we'll be dotting it with dx. But because that path is the exact same, when we go this way, we just subtract it. So it cancels out. So the potential, yeah, it does show up, but in such a way that all the arbitrariness of the potential, it cancels out perfectly.
Okay.
It's a geometrical quantity involving A that has taken care of, for which all that residual ambiguity has literally canceled out.
The potentials being physical might sound strange, but the second interpretation is even stranger. Physicists in Camp 2 maintain that potentials really are just mathematical objects, and the fields are responsible for the effect. But in Tonomura's experiment, the magnetic field was completely confined within the solenoid.
Try to imagine what it's like being the beams combining at the end. Right? They have slightly different trajectories based off of the magnetic field lines that are twisting as they do. So it's as if the entire apparatus is not in the same location, but it is slightly tilted into a different direction. So with the magnetic field being introduced, it on the outside, everything shouldn't just like expand and contract. It's that both of them get a bit of a twist in their pathway. Although you said this whole thing about expanding and contracting, the end result is you get basically a shift in direction, not as much up and down. But the second experiment showed that you also get that. So obviously, whatever's happening on the inside of that toroid is that it has its own energy. So all of the bits that came in through that had the extra bump that when combined with a regular, you can like visualize the different sizes of them, right? And combine them together, and they should end up with the distribution being this one has a bigger bump that it can add to everything. So it will push everything with a different interference pattern. Again, you've only added a bit of energy to its motion. And in this case of the second, the thing with the ring is that you're adding it all in this one area, and everything else on the outside all separate with their own. But what I didn't notice is you would think that on the outside of everything that ring affects the interference pattern should be influenced circularly outward with less and less effect the further you get away from the magnet. And instead, there's only an effect inside of that circle. When we saw the black and white lines, and it was all vertical, and it was like, oh, this one was here, and this one was phased out, right? Well, what is not happening to the outside edges of all of that distribution? It would seem that there should be something happening there, but it's flat, as if nothing is affecting it whatsoever. So, that's curious.
For this interpretation to be true, its supporters are forced to assert that fields can act non-locally. That is, a field can influence things outside the region of space where the field itself exists. Many physicists...
Okay, first of all, you're assuming that there isn't a field that can be influenced by that is extending from the electrons themselves to that wire. And of course, there is a field being influenced by the electrons as they go through space. It is the static field, which is just everywhere. And when electrons go through it, they're interfering, they are manipulating that field as they pass through. So there's this whole thing of what happens to the area around the beam as it's moving through. That's a part of an analysis of this test and everything about it that wasn't even close to being looked into. You're not even thinking about the effect of the beam itself in the local area space. You didn't ask that question. Which is what I've been trying to have you do for freaking 10 years now. The double slit experiment is the same thing. It's the electrons making an interaction with the electromagnetic field that is everywhere. As it goes through, the field itself is like a fluid and it flows with it. So, with the wire in place, with its magnetic moment, it affects all of that. And if there's a small amount, then it drags a bit. Or it pitches it up. And it's this thing that it's like, you're not asking the right questions of what does the electron beam do to the environment? Like, what would magnetic filings or whatever the hell that stuff is? I want to say oobleck, that's the wrong thing. That's the stuff that you punch and it stays solid and you push through slowly and it's a liquid. That's weird stuff. But anyhow, cornstarch and something. But like, it's this you understand it's the magnetic ferrofluid. That's the word. Figure out what's happening with the beam with the ferrofluid, or the magnetic filings, or freaking pins, or whatever you want to do. Have all these bits of information about all the definitions of the parts that you're working with. Otherwise, you're acting on lack of information and no actual assessment of what has happened is accurate unless you have all those different components. You're just making stuff up sometimes.
Find this idea difficult to swallow.
I think the idea of saying that these fields act non-locally undoes the reason why we have field theory. Right? The great triumph of field theory, which has served us so well for more than 100 years, is this stubborn notion that local causes yield only local effects.
And yet, Aharonov's own perspective has shifted from Camp 1 to Camp 2.
When we published the article, we called it the effect of potentials. When you use potential and use the Schrödinger representation, it looks as if everything is local, but it's misleading because that local potentials are really not physical. Later, I decided that it should be called a non-local effect of the electric and magnetic field. The electron can feel the effect of a field that is not where it is.
While non-locality remains a controversial idea,
it's not that it's not local, it's that the local effect is wider than you expected. Or to say that there isn't also another field that it's interacting with means like you're just missing half of the cogwheels that are turning and you're just thinking about one type of cogs. And fuck it.
a sizable portion of physicists do side with Aharonov, and the debate continues to this day.
I maybe have a third interpretation.
Good.
And I would love to get your thoughts. And if it's bad, please tell me honestly.
Okay.
So we did this other video about particles essentially exploring all possible paths.
They don't do.
And so right now we're saying either the potentials are real or fields are acting non-locally. But what if there's a third option where the fields are still local and it is the fields that are affecting the change, but rather it's the particles that are exploring all possible paths all at once? You could potentially even have some quantum tunneling effects going inside an area where there are fields. You know, as the electron or the wave function at least explores all possible paths, gets influenced by those slight bits where the wave function is inside the field.
Actually,
it's way more simple than that. The energy of the rotating magnetic field, as long as it's actually rotating in that direction, is going to give the push on one direction and a pull on the other direction, so it all looks like it's shifted in the tilt, right? That's what it looks like when it combines. It's super extremely simple. And somehow you're like, oh, something about quantum tunneling, blah, blah, blah. Honey, let me explain something to you about quantum tunneling. If there was any, we would see stuff going through it. When we saw that black and white thing, right? Big circle of black, meaning a physical substance in the way of the path. No dots. Do you know why? They didn't do any of that. So, quantum tunneling, not a part of this entire thing. You're just throwing things out there, which you're allowed to do, but you have to properly analyze and not just say things. Especially when you're making a video, why would you not properly do, like, how can you start with a body of work as defined as all of this and end up with a back of the napkin, zero effort in approach? I don't understand how you can possibly do that, because I'm already seeing how this even works in a general sense. But the main thing that, again, the EM field is affected by the beam, or the individual electrons, or the question is, how dense is this beam, and how many electrons or whatever else. Doesn't really matter, because it forces a certain amount of electromagnetic field around it. So if there's another electromagnetic field, then it should have the phase kick, the twisting. I'm trying to understand all of it in a way that's like, there's still some things that are is it actually off or is it normal? I'm like, ugh.
Don't think that's ridiculous, Casper. That's for a strong ringing endorsement. I think there's a lot to that.
Okay.
If we could think about these things as it is indeed the quantum phase that's being affected.
Yeah.
We can describe that phase in terms of quantum mechanical path integrals. I think that's a perfectly reasonable way to frame it. So, yeah, I'd buy that.
That's awesome.
But the problem is, again, particles don't take every path. They take obvious, direct, influenced paths that are not of the actual wavy nature. The wavy nature is part of the EM field. Again, the particles do a separate thing, running alongside of it. Like, it feels like we got this whole song and dance, and it's like we're building off of the same wrong interpretation of, does the electromagnetic field get affected by electrons? Absolutely does, because that's how the EM field is, the way that they connect to protons in the first place. And it is the way that you have electromagnetic fields by moving the electrons that makes the power of a magnetic field big enough that you can just ramp up the power, and then the magnetic field explodes so huge it can pick up a car or a goddamn boat. And trust me, a boat is huge.
Pretty sure this isn't the complete answer, but one thing which would be cool is if someone else takes this idea, or maybe gets inspired by it and they're like, actually, that doesn't work, but here is how it does work, and now we're closer.
That's right. That would be the best possible outcome. Well, the best possible outcome is you're just right. But the second best possible outcome is that nudges the community more broadly to ask new questions of familiar material.
I started with $1 and there's thousands of games.
That's right.
one new question the community asked was, is there also a gravitational version?
In 2022, researchers at Stanford tested this. A simplified version of their experiment works something like this. They shot up ultra-cold rubidium atoms into a tube-shaped vacuum chamber, at the top of which was a tungsten mass. Now, atoms, like electrons, are also governed by a wave function. So they split each rubidium atom's wave function into two distinct packets, and they launched them to different heights. One was sent really high and got close to the mass, whereas the other didn't. And then when the two collided at the bottom, this created an interference pattern.
And when they let this interfere and accounted for all other effects, they could clearly see the phase shift as predicted by Aharonov and Bohm. So it seems like the gravitational Aharonov and Bohm effect is real. If the results hold up to scrutiny, this is a huge finding, because it suggests that the electromagnetic and gravitational potentials can influence reality at the most fundamental scale, even when all the fields are exactly zero. So does that mean that most physics textbooks are...
Yeah, you're saying it's zero. It's not zero. You even said that there is a curl line, which is, again, part of the field. I don't... whatever.
wrong or need updating?
Don't throw out all the textbooks. They're beautiful. We learn a lot, but that doesn't mean we're done. And we should be open to surprise. And just because things haven't changed in, let's say, 200 years, roughly between, say, Lagrange and Aharonov-Bohm, they still could change, right? And they can sometimes change in beautiful and surprising and very powerful ways.
I read somewhere that the reason you decided to do the AB effect was that you didn't really think potentials were something that was just a mathematical tool like most scientists believe.
That is correct. I was very ignorant. Luckily, sometimes it's good not to know too much.
So that was frustrating. That's also frustrating. Swear one of these days they're gonna actually look at my comments and be like, oh fuck. My usual signature. Well, yeah, they keep forgetting how the EM field is affecting things in a general sense, not just like whatever's happening with the two combining beams and the EM field, which does its own stuff and things. You're just forgetting that you did make a magnetic field to begin with the iron rod, and you didn't negate the magnetic field, you created it. And anyone doing basic, like, just iron filings or whatever the ferrofluid stuff would be able to tell you exactly how the magnetic field lines work versus what you've actually designed. And yeah, a twisting coil is going to have that spinning rotational energy stuff happening. Meh. And maybe it has an effect that's wider than you expected it to be. That's not non-local, that's extended local. Whatever.